Right. Yeah. Welcome, folks, to another series of extended mathematics. This time around, we're targeting functions and transformation. Remember to like, share, as well as subscribe to the channel so that you can receive notifications as we do releases. In this series, let's have a look at what you're interested in. We want to say by end of the discussion, one should be able to construct table of values for functions in the form ax to the power n, where n can be integer, that's from -2 up to around +3 there, you name it. Should be able to recognize and sketch graphs of linear, quadratic, cubic, reciprocal, as well as exponential functions. And also one should be able to interpret the root, turning point, asymptotes, and also solve equations by using the graph. In other words, you try and predict where along the x-axis that particular point of interest might be. Also looking at graph transformations, exponential growth and decay. Now, the key concepts that we want within this discussion is that a linear equation is any equation that forms the form y equal to ax plus c, where a, the coefficient of x, is the gradient, and c is the y-intercept. So we have variables x and y. Then on the quadratic, we have a squared plus bx plus c. But remember, when we complete the square, we're able to pick turning points as well as points of interest. Like if you equate y to 0, you'll get the solution to the quadratic equation. Then we also have a cubic graph, which is in the form y equal to ax cubed. That will give interesting introductions to what you might find in advanced levels of functions. Also, the reciprocal, where we are looking at graphs that forms or takes the form y equal to a over x, which we normally refer to as hyperbolas. These are graphs that exist in two parts. So we can look at one where we have a over x, or also a over x squared. Then exponential graphs, these are curves where we have a graph taking the form y equal to a b to the power x plus c. So we're going to look into all these curves in detail. One method of trying to come up with a picture of the function itself on the Cartesian plane is by completion of a table of values. Then you plot to see the shape that the graph would take. So key features of graphs that we might be interested in. When we are drawing or sketching curves, we might be interested in points where these curves crosses either the x or the y-axis. So we call them intercepts. Also the shape of the graph. Does it have turning points? Is it an increasing function, decreasing function? Also, do we have asymptotes, which are lines where the curve will not touch? And sometimes we might be interested in behavior to say if we were to extend either the x values or y values to infinity, can we predict the shape or the picture that the function would take? Then we might also be interested in looking at change in position, change in shape. That's called transformations. Given a function y equal to f of x, if I do a sum to f of x, either a sum or a difference, I mean, this is going to give us a vertical shift. I mean, it's a shift within the y-axis. But now, if we come inside the brackets, as if we are substituting f of x of a new function, x plus or minus. So this is going to give a horizontal translation where if you say plus a, the graph shifts to the left. You say minus a, it actually shifts to the right. Then we also have y multiplied by a multiplied by f of x. This is a transformation which gives us a vertical stretch. In other words, if we've got asymptotes or turning point, I mean, maximum or minimum points, when we multiply them by a, it can be a stretch factor, either positive or negative. Then when we look at a coming inside the graph, this is going to give us a horizontal stretch to say on the x-axis, do we stretch out or we stretch in? Now, we are going to quickly jump into 10 worked examples. We'll be discussing about them to just have a sense of what we are required to work around. Here we are given an equation of y equal to x squared, and we're given the values of x running from -2 up to +2. So when we do a substitution like -2, if you substitute for x there, you square it, gives us +4. So we can see that this graph is symmetrical about the point 0. In other words, the y values, if you check, they are the same either way. So when we draw this sketch, I'm sure we'll get a picture generally like this. That's x, y gets something of this nature. That's y equal to x squared. We call this graph a parabola. Right, next we're moving to a cubic graph. We're given a function y equal to x cubed, and our interest is to sketch. So when we are sketching this curve, I mean, we are going to get something of this nature. That's x, y. It's more like it's a graph whose point of inflection is at the origin. As well as turning point itself is at the origin again. Quite interesting in the picture of the function. So this is a cubic function y equal to x cubed. Still moving on. Reciprocal function, which we normally refer to as hyperbolas. So hyperbola, this is a function which exists in two different paths. It can be first, third quadrant, or it can be second, fourth quadrant. So for this case, that's y equal to 1 over x. And this denotes our a. If a is positive, you'll find the graph in these quadrants 1 and 3. But if a is negative, a less than 0, then you'll find the graph in this particular marked point. Then the fourth example, and again, one thing to note is this graph, which is called a hyperbola, it has got lines that we call asymptotes. In other words, these are lines the curve will never touch. It might get as close as possible, but it doesn't touch those points. We ended in a sketch again of y equal to 1 over x squared, similar to the one above, but one thing of interest is this curve does not exist in the negative y. So in other words, we are going to see a picture like this, which was the initial hyperbola, but the other part it will come this side because it doesn't exist in the negative y platform or region. Right, then next we have exponential growth. Here we are interested in just a sketch, and when we say sketch, we're saying roughly how does it appear. So the sketch is going to be, because we might be interested in testing with a table of values, but I think we can see that as x grows, that's the base 2, will be growing binarily. So here, somewhere where our x is 0, it will be 2 to the power 0, that's 1. So this is just a curve which goes like this. That's y equal to 2 to the power x. Then next, moving on, exponential decay. You see when our b here, which is more like our base, if it's a decimal fraction, we have exponential decay. In other words, it looks like the picture is going to be reversed from what we had above there, because we are saying in the negative space, that's where the graph will have rapid increase. So it will come again through this point, but it will decrease generally going downwards. That's why equal to 0.5 all to the power x. Then moving on, finding the roots graphically. So if we are finding the roots graphically, as we can see, this is a function which is similar to that of y equal to x squared. But according to transformation, if we put minus 3, it means we have dropped it down 3 units. So if we are to sketch the picture, it's going to be x, y there, somewhere where we have y is minus 3. It becomes our turning point like that. That's y equal to x squared minus 3. So if we are asked to solve, in other words, we are looking for the intercepts with x-axis. So if we're to solve algebraically, we are saying x squared is equal to 3. Therefore, x will be equal to plus or minus root 3, which I think roughly approximates to what we are given there. Then next, we are interested in turning point. Turning point, we normally get it from completion of square. When we are completing the square, I mean, here we are going to end up having x 2 there, and then we put squared. There is a plus 3. But remember, if we are to square 2, it will give us the last part, which was 4. But because it's not there, we're going to say minus 4 plus 3. And in the end, we end up getting minus 1. So when we complete the square, it's x minus 2 squared minus 1. So this is the q point, which is the coordinate of the turning point with p, q. In other words, if I'm to put it in coordinate form, it's going to be 2 minus 1 like that. Then next we have transformation. We are interested in moving from graph of y equal to x squared to y equal to x squared plus 3. So let me bring my Cartesian plane or xy to say, but the function y equal to x squared is like this, y equal to x squared. But now, if I move to y equal to x squared plus 3, let me pick a black ink and say, but somewhere where we have 3, that becomes the new turning point because it's a vertical shift. It will be like that. That's y equal to x squared plus 3. Combined functions. We have got an interest on drawing this graph where we have x squared plus 2x. This is a parabola with a root set 0 and minus 2. But let's try and check how this parabola would have looked. If I'm to sketch the picture, it will be something like this, x, y, but I want to complete the square. So when I complete the square, this will be x plus 1 squared. But now, if I square 1, I don't see it, so it will come there so that at least we have the similar picture that we're seeing there. So what's our interest? This is going to be our P and that's our Q. In other words, the coordinates of the turning point are going to be -1, -1. So if I'm to sketch this parabola, it was supposed to be having a turning point at the origin. Normally that's how a parabola would look, which is y equal to x squared. But check here, when I say plus, it means it's a shift 1 unit to the left. So where it says -1, it means that's the first shift that we have, horizontal shift. But then there's a -1. It means finally it will drop down to -1 here. And I can bring the black color now to say, but this is going to be a curve more like that, where these coordinates of the turning points are going to be -1, -1. So I'll name this curve to be y equal to x squared plus 2x. I think basically that's it on our introduction, folks. I hope you found this informative and also assisting. Let's meet again in the second part where we are going to be discussing with similar problems to the one that I've done already. Please remember to like, share, as well as subscribe to the channel so that you can always receive latest updates when new recordings are done. Bye for now, folks.